So, hi everyone. Coming. Our speakers today are actually just one speaker, Ritesh, fantastic. Uh, my friend with the WINLAB alumnus did his PhD under Jack Coach, and Ritesh graduated with his PhD in electrical engineering from Stanford University in 2006. They both now work at Qualcomm-Flarion Technologies, and Ritesh will be talking to us today about distributed interference management and scheduling in wireless spectrum networks. So with that,
Thanks. So in this talk, what we'll try to do is look at some of the techniques we've been using for interference management and computer networks. And the main motivation comes from a practical setting. So we've been using theory which exists and trying to adapt that in a practical setting. There will be some challenges for development and in terms of how you design the correlation. So let's just first start with a very brief overview of what we mean by computer networks and what a typical setting would be. So computer networks are essentially low-power access points to be used in homes and offices, and it'll operate over licensed spectrum, use cellular technology, and it won't be planned. So you just deploy it, it should organize and coordinate all the different services that should coordinate among themselves. And the main motivation is they provide better coverage. So getting coverage at home becomes much easier, and they provide capacity gains via spatial reuse. And this can be used to reduce basically the cost of getting wireless access. So this talk is mainly on the technical aspects I won't be addressing.
So therefore, all the links shown there are completely in licensed spectrum, right?
So the links
At least in
can sell to everything is unlicensed spectrum. And this is essentially connected over the internet.
It's all
Connected over
it's an on license. On license.
Okay. Sorry, one thing.
No, that's what I was asking.
So others are wired.
Yeah. So there's a femtocell which communicates with a bunch of wireless devices connected over via backhaul to the internet. So it's connected to the router, which is
So there's one femtocell in every house. That's all going on.
one at least.
One at least. Okay.
I mean, depending if it's an office building, you may need multiple femtocells.
It will be pretty much like the way your DSL router.
So your neighbor could have the same thing on the same spectrum. Yeah.
So I think this is a very not relevant to this, but who do you pay this? Like your internet service provider and
So all that is actually, we can give you some option offline, but if you get into that question, we'll just go on a tangent. It's a very interesting question. It's not fully resolved, but it's a lot.
but we say it's cellular technology, right? So sort of all the kind of control channel signaling stuff and all the stuff you normally do, right, in your backhaul and all that, and somehow you're going to do that through public internet. And I had the impression that base stations do things with sort of timing and that are sort of seem like a stretch for.
So you mean things like synchronization across different base stations. So we want to address that, but you would do it either using over-the-air technology.
So you do that over the air, not through.
Depends on the backhaul. I mean, that's again, you can.
The synchronization in many of these boxes, first of all, for the 3GPP technologies, you don't need synchronization. For the 3GPP2 technologies, synchronization can be provided either if you can see GPS, then you use GPS, and many of these boxes come embedded with GPS, or you try to synchronize to a macro cell that you can see. So many boxes come with this feature called network listen, which allows the femtocell to behave like a mobile, just for the purpose of getting synchronization and frequency stability. And there are options based on IEEE 1580 PTP based synchronization, although it's not clear that would be adequately fine resolution. So for example, the network extender box of Verizon cells actually comes with instructions on how to hook up the GPS. And there is apparently an LED on the box which shows whether you're able to get GPS signal or not. And if you don't get a GPS signal, then there are some instructions that the user follows, where he goes and keeps the antenna close to the window or something, because there's a cable provided to get the GPS signal.
Sorry.
But we're also looking at self-synchronization techniques from the research perspective.
Sorry, Ritesh.
No, that's
This is, people care. So they ask me to so the Femto cell that you label there, that's what Verizon will sell you?
Yes.
Okay.
So you can look at this network.
And this router can be like your home, whoever is providing the broadband router can be your cable, whatever.
They're decoupled.
Okay.
There's a lot of interesting QoS management issues that come up.
Sure, yeah.
So, before delving deeper into what challenges of Femto networks are, let's first just take a step back and see what do we do for interference management in a cellular setting for OFD networks. So, the good thing about macrocellular deployments is they're planned very carefully, so that helps you ensure coverage and get decent assignments. And also, what typically happens is a mobile would associate or communicate with the base station that is the strongest for it. So that already implies that the interferer is going to have a weaker signal here compared to the serving base station. So that already helps quite a bit. And then the techniques which help you serve users which could be on the edge of the cell where the interference could be still significantly strong. So what you do is essentially do some semi-static partitioning of resources across adjacent cells. And there what helps again is because you have many users in a cell, you get some statistical multiplexing gains, and hence you only need to do the semi-static partitioning over a slower time scale. So essentially what you're doing is some variation around the previous one over slow times. So this example, for example, most of the resources are shared by both the cells, and for edge of cell users, you would orthogonalize on some side of the cells or do some power control.
So this is done dynamically.
Over somewhat dynamically, but may not be at the level at which you make assignments, at the level at which you assign resources to individual users. It may not be as fast as that. Because there are multiple users in a cell, even if two of your mobiles don't need to be served at this point, you can use these resources for someone else. So resources don't do this. But if you had only one user, then things would be different, because if you're not serving it, you should just relinquish the resources and give it to the other side. So that's what essentially happens here. So the two things which make the interference management more challenging in a Femto scenario. So the first thing is that it's essentially an unplanned deployment. And you could have a constraint that you're allowed to associate only with the object, which makes things even worse. So for example, it's just a simple figure which illustrates that. This mobile is actually closer to the Femto cell here, but it will be forced to communicate with its own Femto cell. So when it transmits on the uplink, it's going to cause a lot of interference to the adjacent Femto cell. And also, there could be very few mobiles in a given Femto cell, so you don't really get statistical multiplexing gains. You need to do this coordination at a much finer bandwidth, otherwise you'll be wasting resources. So you want to be able to grab resources and relinquish them at a much faster time scale compared to the cellular setting.
So there's low statistical multiplexing. I want to make another point that in the macrocellular networks, typically you assume that you don't have a dominant interferer on the uplink. You have an aggregation of interference. So anything that you measure in the current time sort of applies, is highly correlated with what you get at time t plus delta. So some user goes down in power, some other guy goes up in power, because of large number of users contributing to interference. You can actually come up with control mechanisms on the uplink which are based on measuring something that happened in the recent past and then taking action accordingly. One example of this is in CDMA systems where you control the rise over thermal noise and try to keep that at some reasonable level. Here it's a different ballgame, because now you can have the notion of a dominant interferer, and something that you measure at time t could be totally different from time t plus delta.
That's because of the traffic or it's because of the unable.
It's because of the traffic and because of the fact that there is much more likelihood. For example, in this picture that you've shown, which is a simplistic drawing, the bottom right-hand base station, it matters a lot more for that femto cell whether the mobile just next to it is transmitted. It matters less whether the guy on the far right top is transmitted. That's one reason. And also because if the spatial reuse, everybody is getting somewhat of a fat time. So your duty cycles on each of these links go down. So both of these add to the variance of interference.
So what this illustrates is we need mechanisms for interference management at a fast time scale. So you should be able to coordinate across cells and need to be optimized. But we need to be a little careful in the way we do that. And we should, if we do too much orthogonalization, it can actually hurt us. Like this is a plot that just shows that you need to be somewhat close to reuse one, orthogonalize only when the SINR is bad. So the x-axis shows the user SINR in reuse one. So this essentially assumes that all your interferers are transmitting at full power, and this is the SINR you get. And on the y-axis is basically an SINR improvement when you orthogonalize. I'll explain that in a bit more detail. So let's first look at the blue curve. What the blue curve assumes is if you were to orthogonalize the transmission between your own cell and an interfering cell, you would get half the packet. And on the y-axis, what it's shown is the SINR improvement that you need to break even in the rate to compensate for the loss. So if your SINR is pretty good, let's say even 0 dB, you need at least 5 dB of increase in SINR when you optimize just with one user. And if you have more users, if you go to bandwidth, say 1 by 4 or 1 by 8, you need much more gain in SINR. So you should be very careful when you go away from reuse. That's kind of the main message in this one. So essentially what we need is coordinate transmission at fast time scale across multiple cells, but the user spectrum should be efficient. So whether you orthogonalize or whether you reuse one should ensure that you're operating close to the maximum spectrum efficiency. And another thing is we want fairness across cells. So in a macrocellular network, you would get fairness just by doing some semi-static partition. Here you get efficient user spectrum and fairness. You need to be much more dynamic compared to the multi-cells. We should be able to meet QoS targets, delay targets, but at the same time, the coordination mechanism across cells should be very low. But if you invest a lot of resources in doing coordination, then it's kind of pointless.
So is the assumption in the femto cells that it has essentially the same frequency available that the regular cell tower has?
Exactly.
So therefore it has the entire spectrum available.
Yes.
And this orthogonalization is relative to other femto cells or in relation to the macro cells?
So it could be one or both. In this talk, we only focus on femto cells. So we don't look at the macro versus femto issue. What would help you there is because you get statistical multiplexing in a macro cell, and you get, when a macro cell you transmit something, you cause interference to a bunch of femto cells, you again get some statistical multiplexing. So this coordination potentially could be at somewhat a lower, slower pace.
And you're just thinking about this for CPU basis.
No, this is all OFDM. This talk is all OFDM.
It is. Okay. I wasn't sure. You first nodded yes, then you shook your head. No, I thought
So
maybe one of those two answers.
So this is a Qualcomm versus Flarion.
This is
I don't think that's. The point here is that basically the level of abstraction at which we're treating this is there are a bunch of frequency sets or subbands, and you're trying to figure out how many of these subbands you can take. Now, so it doesn't really, you can't build it as CDMA or OFDMA. It's just that in OFDMA you can go to a finer granularity. In CDMA, for example, if you take the North American CDMA of 1.25 megahertz, potentially you could do this with multiple carriers of 1.25 megahertz. So that would be a way to do it.
but all the explanation, everything is at the back of the mind is OFDM, but you could expand it to any other.
So when you talk about the difference management of the macro cell with the subcomputer cell, again the macro cell has to coordinate with these cells to do what. Anyway, I mean you're not going to talk.
We won't talk about it, but the thing is, it's in some sense it's easier because you get some statistical multiplexing at the macro cell and among the macro cell. So you only need to coordinate when femtos can transmit and when a macro cluster of femtos can transmit and when a macro can transmit. But in a femto cell, you have to coordinate. If my dominant interference is on, I can't go. But if my dominant interference is off, maybe I should go. So that's that granularity or the time scale at which you do the coordination. It's much faster. So that makes it harder. But in this talk, we only concentrate on coordination. The last point is we want an algorithm which should adapt to different interference scenarios and traffic types. So if you have low interference, it should only use one. If you have high interference, it should not use. So natural question one may ask is, why not use Wi-Fi the way you've been using it so far? And that's an interesting question both from, again, technical and business point of view. We'll concentrate only on some of the technical aspects. So Wi-Fi essentially allows you to coordinate at a very fast time scale. You grab the medium if you want to send a packet, and once you're done sending the packet, you just give away the medium. But it suffers from quite a few problems, and I'm sure most people in this room are aware of them. So the couple of problems is the spectral efficiency that you can attain is not optimal because it does too much optimization across transmissions. And then it suffers hidden exposed nodes problems. You can solve that, but you can't at some level that problem solving. And fairness control with the current technology, you don't have enough hooks to do fine-grained fairness control. So potentially you can put in some other things. And range and unequal transfer powers are issues. There's some ways you can get around unequal transfer powers, but range is essentially an issue, fundamental issue of the technology. You can't transfer at very low rates. But the good things are, it's very dynamic. It works in any kind of deployment. You don't have to sit and plan what you're going to do, and no synchronization is needed. So what we want to do is essentially take some of the good points of Wi-Fi, combine it with cellular kind of technology with the appropriate control channels, channel feedback, and so on, and design a map for campuses. And in addition, what we'll do is actually we'll add fast inter-cell coordination across cells, which doesn't exist. So fast inter-cell coordination to achieve fairness. So that is, in some sense, so before we go into the heuristic we design, I'm just going to briefly go over some of the literature that exists and some of the techniques which can help us in actually designing the algorithm. And a very brief overview, it won't be complete, but it will give us some key ideas which will motivate the algorithms later. So let's now step back and just go to a somewhat abstract setting where we look at end wireless links, and essentially we model the serving link gain and interference link gain via the matrix G, where Gij is the channel gain from transmitter from J to receiver. This is the standard notation we use. And then the rate that you get is just a function of the transmit powers, and it depends, rate that one link gets depends on the transmit powers of all the links. And what we want to do is essentially schedule transmissions of traffic. And we want to do this for a couple of different objectives. So we look at two different kinds of traffic. The first kind of traffic is best effort / full buffer. And here, the way we model user experiences via some concave increasing function of the average rate that the user sees. And the second class of traffic we consider is delay sensitive QoS. The user function just depends on the delay CDF of the traffic. and this would you would typically use an open loop kind of traffic noise of each. So for best effort traffic, we can look at a gradient ascent equation. This is not the optimal way, or the computation is not actually, the computation is actually pretty complex, but this will actually motivate some of the algorithms to look later. So let's not look at the deficiency in the sense this will be complex, etc. But this will motivate some algorithms. So what we can do is at each time select a transmission power which maximizes the derivative of the equilibrium function times the rate that the user will see as a function of the transfer power. And then we keep iterating. So essentially what it's doing is picking a transfer power which leads to the maximum increase in the equilibrium right rate.
So this rate region is it will it go on hit the global optimal or this?
Will it go at a global optimal? I don't know. It's just doing an increase in the maximum increase. So the rate region is convex, but the rate region is not. No, rate region is.
No, but I mean here because your powers are variables, I think it's
Always in the denominator.
it's not.
It's not. It's
Anyway,
I haven't looked at it.
I think that's not good.
So what is B?
Oh, B is the total matter. So this is just spectral efficiency. The way you operate is some normalized spectral efficiency times the matter.
And RI is the rate, and XI
Is the average.
wait.
So RI is probably spectral. RI is
RI is spectral efficiency, but here it doesn't matter if you put spectral efficiency or spectral efficiency times 1 pi.
and that units
So
to
for units or the utility function.
Sorry, what is XI?
XI is the average rate that it uses
Over time or across the
over time. So you update it using which will be
So RI is actually bit specific. And
RI.
XI is bit specific. Because if you're making a bandwidth for something,
You're making a bandwidth?
No, you're making a power
here we
bandwidth.
make, yeah,
That's it.
I think later on.
You could have zero bandwidth, but it's zero.
So this is just a power update, right?
This is just a power update actually. And essentially you're taking the power to maximize the gradient of the increase of the function. I'm not
It's centralized.
This is centralized. This is efficient.
It really matters on what the initial conditions are. I mean in this case.
If there's no global convergence, it matters. So actually fairly sure I can show convergence in this specific, but let's look at what this algorithm does just to get some feel for the utility function we should use and how it can actually be used in this. So this magenta curve shows the rate CTF when you do reduce one. So on the x-axis is the spectral efficiency across links, across multiple drops, and by drop what I mean is I drop n femto cells in a region, n femto base stations and mobiles in a region, and look at the spectral efficiency you get if everyone transfers on it. So this magenta curve shows the rate CTF. On the x-axis is spectral efficiency, on the y-axis is the CTF. And as you change the utility function, you can actually make the CDF less fair or more fair if you run the iteration shown on the previous slide. So if you do proportional fair, which is the black curve here, what you do is you pull out the tail quite a bit, so you increase the rate of the users with low spectral efficiency to use one quite a bit, and you sacrifice some rate for the maximum efficiency. And then depending on the choice, you can make it more fair or less fair. So if you go to x to the power 0.5, or I think this is x to the power 0.5, more unfair, which is blue color. So you pull this less, sacrifice less.
There is one user per
One user.
and they don't have any minimum rating.
No, this is just looking at to use one versus between
Full
different
buffer.
functions. Full buffer. Now, if you look at delay sensitive QoS traffic, again, this is also standard what an iteration which would stabilize the queues is one where you actually just pick the power as R mass of this function, where f of qi times di is a function of the queue length times the head of line delay at a given length. And Ri of p is the rate you get if you pick the power p. And what you're doing is essentially picking a power which maximizes this max rate, standard max rate. So you go to Q length and reduces to decimals. And you do this over small resources each time, and you keep doing it iteratively and essentially stabilize the queues. And depending on what function you pick, you can actually control the delay CDF to some extent. So there's empirical studies to show you could pick different functions and different delay CDFs. So just some, again, simple example, 9 femtocells, and we look at the delay CDFs. We're using a couple of different functions there. So this is some low loading scenario where if you use the max iteration, you get delay CDFs which are red and green. Red is for B, green is for long. They're essentially similar in low load. And reuse one just collapses for even though they're not full buffer, it just get collapse. So you do need partition this. Now when you increase the load, something interesting happens. If you use log of P, it leads to more graceful degradation in the delay CDF. The reason for that is log of P, even if someone's delay starts going up, you compensate, you try to bring it down only if it goes up a lot. But if you use a function P, the moment your delay starts increasing, you'll quickly try to pull it down and you'll sacrifice the delays even of the users which would otherwise get pretty good performance. So log of P at this boundary region leads to more graceful degradation compared to P. So depending on what function you use, you could get, and what scenario you're looking at, you could probably get different degradation.
I'm really puzzled by the second graph. That's a CDF of delay. Is that right?
That's actually
both graphs?
no. It should be, sorry. There's a typo here. That's a good one. I should explain that. So the x-axis is the CDF of 90 percentile delay across users. So look at a user, look at its 90 percentile delay. Go to the next user, look at its 90 percentile delay. So it is the CDF of these 90 percentile delays across users.
Okay.
So what I'm essentially assuming here is that performance depends on a 90 percentile delay. If it's bad, it's bad.
So again, I want to.
Maybe you can ask the same question.
No, I had some other question.
Oh, okay.
No, you can ask yours.
No, it's okay.
So they're basically each link is sending certain number of packets in this information. You're counting the delay for each link and plotting the 98% CDF on the 98% delay across multiple links across multiple accounts. So what's happening, I think the main thing this is illustrating is how the log P retains some robustness putting the low load to the high load and keeping that 98% reasonable. It's less sensitive. That's
And the user which are in bad interference, it just lets the delay grow much more. Whereas if you use D or D square or something like that, try to bring that down.
But some of these CDFs never seem to get here one.
Never seen?
Yeah, I think the high load, the delays are very large.
It's very large.
So it's showing only a
Fraction. So if you had
small fraction. Which actually illustrates the important point because I think there are only 9 links here. And based on the interference condition you can really get some very large packet delays for certain features.
So I mean, I see. I mean, there's some, a 90th percentile delay is the 90th percentile with respect to the delay seen by the packets of the individual user.
That's right. And then you look at the
So we are
CVF.
looking at this graph, which is all about for the blue line, 30% of the users, right, have 90% of their packets delivered in less than, delayed 250 milliseconds. So it seems like an unusual way to describe things, doesn't it?
So the reasoning behind this is if you look at voice or video, what you want to control is essentially the 90th or 95th percentile delay. That's how it is in standards you specify the QoS requirements. So what it shows is 40% of the links, say in the green curve, 40-45% of the links have acceptable 90% delay. But I could have had another set of plots showing the delay across all the packets.
So the 90% of included with all the simulation that Chandra used to do with.
No, but just 90 percentile is 90 percentile within one user. Chamfer's was 90%
Across.
They across the users wanted to give 90% of they would throw away 10% of the users and say for 90% of the users we'll try to give them some good high rate, like in some network MIMO or some relay rate. Like the guys at Copper Hill are always designing systems, right, where they want to provide the service, and what they say is, we'll throw away 10% of the users who are kind of making our lives miserable, right, and we'll provide good service to the other 90%. Right? It's the sort of the opposite of 90%.
But this shows similar thing if you use a log versus beam. If you use a log function, what it will do is it will throw away. Here it's kind of almost like throw away 50% of the users, but I'll serve 50% of the users and acceptable keywords.
Then your scheduling is not stable, right? Basically,
It's not stable.
You are working under this. You said you started out with okay, I want to find a stable scheduling policy, and then do this.
Yeah, no. So stable. I mean, this is low load. If you could get close to high load, I mean, close to the stability region, maybe you'll see some difference in the data. But this is clearly unstable. So if you had an unstable system using different functions would actually lead to different degradation in the users. So if you had a case where 10% of the users you could support 90% of the users. Log would help you do that compared to using a function, say d square or something, where those 10% of the users delay going up will start hogging up all the resources, and then that would lead to the delays of all the other users. So there's this inherent trade-off whether you want to control the delays of all the users or you want a scheme where you basically sacrifice some of the users' delays and say, I will support these users. So where you want, I mean, it's somewhat of a design question what you want to operate, but depending on how you change this function, you could lead to either of these.
So the trade-off.
So let's say
I just want to understand the trade-off between the two control mechanism, the control action you take, and what.
So the trade-off is between whether you want to control the delays of all the users or whether you want to, it's acceptable to sacrifice 10% of the users and support the other 90% of the users. So if you do use log function, what it will lead to, even when you're in a stable region, it will lead to more spread in your delays as you get closer to the boundary. D would ensure using D or some higher power.
Boundary of the
yeah.
Boundary of what is when you're saying
somewhere close to the boundary. Doesn't matter at what. If it's a small network, doesn't matter which dimension. So there's an inherent stability region which says the method that whatever 9 people of rates with a given arrival process where you can keep the delay less. So you can keep the queue stable. There's an inherent stability region. right? 90, whatever, 90. Now, if you get closer to the boundary of the stability region, what log will do is lead to a higher spread in the delays compared to using d or d square, which will bunch all the delays together. But then if you get very close to the stability region, just outside, what log will do is sacrifice some of the users and let the other users get decent performance. But using some other higher power of d, what it will lead to is all the users doing badly, or a larger chunk of users doing badly, because the moment one user starts the delay for one user starts increasing, you're going to try and compensate it more by taking your resources from the user.
So these two, the green and the red curve, based on what you're saying, will probably cross over.
Yes.
At some point, log will go to the top.
I just don't have enough snapshots.
But this metric is not unusual actually. This is the one that's typically used for comparing voice capacity across technology. Just keep loading it up, measure the 95th percentile delay, and look at 98% of the user should have 95th percentile delay under some X. That's defined as your capacity, and then you're comparing it with zero. So it is viewed as the right metric for delay sensitive services.
Essentially, what this motivates is that you want to solve a problem where we come up with a simple distributed algorithm to pick power P, which maximizes some weighted sum of the trades. That's essentially what we're going to concentrate on for the rest of the slides. And computation, as you can see, is first of all centralized. You need to know all the channel gains, all the transfer powers across the network, and coordinate these in a centralized manner. And secondly, it's a highly complex computation.
Oh yeah, so I forgot the question I was going to ask you. Came back now. So, so where is the orthogonalization and bandwidth happening? Remember, you sort of had this trade-off, right, between going orthogonal versus the SNR improvement that was required when you sort of were doing that. So I kind of lost that. Where you're doing that.
Here, let's say, look at two lengths, and they're highly interfering. Only one can go at a time.
Yeah.
And one length had a higher average rate than the other length. Then what this would do is look at the link with the lower average rate and let that transfer at max power and let the other link transfer at zero.
Oh,
It's all out naturally.
It falls
All
out from this algorithm
Because this is actually the superset of allocations you get. So by nature, this will try to find very high interference, few link situations. The solution at any iteration of this algorithm will end up being one guy will be at P max and the rest will be at zero. And then over time somebody that who's at P max will change. So this actually will find you that right.
So it's like the transmission more than some
Yeah.
variable cost.
It's like infinite transmission.
Yeah.
So when you say centralized information call center, is it one micro-based station or one micro-based stations?
This is, so let's say we're looking at whatever 10 clusters, 10 campuses in a building, you would need to know, compute RIP, you need to know the channel gain matrix, 10 by 10 channel gain matrix. So interference from each of these pairs of campuses, you need to know. And then you need,
So it's centralized from your choice of the subset of the femto cells in the environment. You choose these 10 cells is something that you want to control.
yeah, so you would have to be centralized across these transfers. So in a building, you don't have to be centralized across all cells, because what happens if you have this cascading effect, one affects the other. So to do this exactly, you would have to do it.
So what is the deployment scenario? These 10 cells are all belonging to the same operator and operating on the same channel.
But we are not suggesting doing this in a centralized manner. What this is going to motivate is some heuristics to do it in a distributed manner, because centralized takes too much time to coordinate and send information back. If you want to do it
Distributed can be access points for femto cells, base stations.
in a very dynamic manner.
Hey, so one more question, right? So the two user example, yes, I got that, right? Sort of essentially your power control will basically tell you the power vector will zero out some of them, zero out one of them, What happens when you have n users?
So
There are more than two. So where is it falling out that essentially, are you still going to have one at a time? Is that sort of what it's falling
no,
out?
it,
No, it's not.
it won't do it. So let's say in end users you had some, for simplicity, assume you had constraint which says pairwise constraint, which says two of these things happen. So from this metric WI times RIP, so it will pick the best combination of links to transmit, which maximizes the summation of WIs over those links. So if two links cannot go together, they're going to totally kill each other. There's no point setting both of those powers. Let's say assume 0, 1 kind of, right? If both of them try to go together, they're going to get 0, right? So there's no point. But you will get a strictly better objective function if you reduce one of the guy's power to 0 and increase the other guy's power to 1. So if you can extend this to an n link scenario where you actually look at some rate region for this. So if you were to do it in a centralized manner, it would automatically pick a rate vector which maximizes this. And if two links interfere highly with each other, you can't have high values for both of them. So you have a choice. Both of those are low, or one is high, or the second is high. So even n tuples, if you had choices, the links with the constraints are more complex, it would say, okay, these set of links can go together, or another set of links can go together. You would only pick set of links which would operate close to the boundary of your feasible rate.
Okay, so therefore, essentially here it's really orthogonal. So ones that are on at the same time, they're all sort of sharing the same.
They are sharing the same.
So it's not like there is some, because I was thinking of OFDMA, right? And then there you could do sort of other fancy things.
No, this falls out of the same thing. Because you have a...
I mean, depending on where spatial,
Yeah.
I don't want to use the word reuse.
Right. This objective function
Yeah.
can be maxed over P comma P, where the vector P is, in addition to a power vector, you're trying to solve for a time vector. Yeah, that's true.
Yeah, but the P is actually an integer vector. Like you have
Both these are.
It's an integer vector, but in reality, even the power thing is the only computationally reasonable way to solve this to have discrete nodes, even for power. Is that clear?
Yeah.
Setup is
So, rest of the talk, essentially what I'm going to do is look at a local coordination mechanism to exchange the right amount of information, and then look at an algorithm which is distributed and basically ties in with this coordination mechanism to try to maximize summation times at each time step. So this is kind of a piece like describes the mechanism that we're using. So for simplicity, let's look at one serving femtocell, one mobile, and an interfering femtocell, and concentrate on the downlink. So the coordination essentially consists of 4 different steps. The first step is the serving femtocell tells the mobile it is serving what its priority metric right now is. It could be based on average rate or based on head of line, delay, queue line, or whatever you have. So essentially it sends that WI to the mobile. And it needs to do that because the mobile doesn't have the queues at its site. It needs to get that information from the base station. Then what the mobile does is broadcast some coordination message to its interferers. So specifically in this setup, it will broadcast this message and it will be received by the interferer. And there are 2 things which it tries to convey. One is its own priority and priority times rate that it will get if it got to go. And the second thing it wants to convey to the interferer is whether this interferer is really a dominant interferer to this mobile. If this interferer is a weak interferer, then this guy may not knock out. So somehow we want to get this information out. And hence we have this receiver-based mechanism where because if the receiver sends the message, you could just look at the power at which you're getting the message and detect all the receivers to which you need to back on. So that gives you some information. Then the third step is all the interferers get this coordination message. So here this interferer gets the coordination message, and as a function of the coordination messages you receive, you decide on the transfer power you will use in a subsequent connection. And you convey that through pilots. And these pilots are measured by all the mobiles in the network. So once the mobiles measure the pilot, they'll feed back the channel quality or SINR to a serving base station so that you can select the appropriate modulation. So this ties in with Ashwin's comment right at the beginning, where in a macrocellular network, if you have also statistical multiplexing, you don't need an explicit feedback. You can just use what you measured in the past. But here, it's necessary because if this interferer transmits, you're going to see a very different channel compared to the case where the interferer doesn't transmit. And this is going to vary a lot with time. So that's why we have this fourth step where we actually feedback the SINR based on the pilots you receive.
So then you have to do all these 4 steps at a fine time scale.
Yes, and you want to keep the overhead for this. So that's.
So there are n such interferers, each one of them will have to
No, this is a broadcast message. And then this is again pilot. So they all come together. You just measure the total.
You think of it as a 4 frame pipeline economics. So if you want to compute for n plus 4, that happens in n, this happens in n plus 1, then everything just slides over.
It will work because they're all synchronized.
Yes, we are
It's a synchronization.
And each mobile has to
each mobile you want to schedule at n plus 4 at n you will send it. So here we have only one mobile, but in a general setting you could have multiple mobiles per cell. So it's tied in with the scheduling algorithm. So probably skip the very similar to the uplink. So we can just spend a minute on. So this what we described on the previous slide is coordination, everything happening over the head. But femtocells, since they're connected by this backhaul, you could potentially use the backhaul also to do some of the coordination. So you could actually split the coordination in the sense you send some information over the backhaul to the interfering femtocell saying I want to send this packet out and back off if you're positive. And then you could have the femtocell signaling transfer power, and then you feed back the channel quality back to them. So you could do.
So does this mean that suppose I have a femtocell and my neighbor has a femtocell? So my femtocell will say to my neighbor's femtocell to shut up. That's sort of what we mean.
That's what's happening.
Yeah.
And there's a provision that allows for this. That's how sort of these things are going to work. What if my
I
neighbor
don't know how
buys
it's
it?
going to work ultimately. This is sort of early days.
Okay.
But the reality is that, I mean, it seems like you can be in one of two things, right? In the Wi-Fi, then you have these rules of bandwidth, and particularly you can be somewhat inefficient in your spatial multiplexing and get away with it. If you go to the femtocell setup, you have a license plan. Spectrum is important, I mean, to use it efficiently, and then some sort of coordination mechanism. So,
No, it's funny, right? It seems like you guys are now working in a situation where you have one or two very few dominant interferers. And that's exactly where I think spreading and multi-user detection and interference cancellation work really well.
they work very well.
They work really well.
Yeah,
I think that you guys should go back to doing that.
So it's yes and no, right? I mean, when you have one base station trying to decode two signals, one is dominating the other,
Yeah.
then it clearly comes into view. Here you're talking about distributed links. So of course these are things we're looking at, but this is another form of interference management that can mitigate it. Those become more challenging when you have those distributed links.
So this backhaul-based scheme, doesn't it sort of go against the initial principle that you had outlined that Wi-Fi has ease of deployment and distributed?
So it's not that hard to figure out your neighbors and communicate with the partner. It's still unplanned and it's you can do self-communication. You figure out who your neighbors are. I don't know the exact optical protocols, but if you could do that, then I mean, there's no planning here. You're already connected to them. But you save resources over the air. You save spectrum for communication. So essentially what you want to do is design an algorithm which actually works in this framework where you exchange the right kind of information which is useful. Now we want to then come up with a heuristic which mimics trying to maximize this function. And the challenges are that we just have one round of information exchange. So you can't actually iterate and send information and get back information because it's expensive and takes time. So you just send out some broadcast message, interferer see it, and they decide the transfer power, and that's it. And each transmitter has only partial knowledge of the network state, channel and buffer states, and there's some delay. So the scheme I described over the air has about 4 milliseconds of delay coordination on mechanisms which are focused to this. So the rest of the talk specifically look at 1 mobile per cell, downlink traffic. So again, these 2 slides kind of contain the product, this slide and the next slide. And after that, it's just simulation. So I'm going to go through this over. So we have one base station I, mobile I, another Femto base station J, mobile J, and we're looking at downlink. So essentially what the steps would happen is if base station I wants to transmit to this mobile, it will send the priority, this guy will broadcast the message, received by the interferer. Interferer will look at its own mobile state, whether it wants to send information or not, and then compare it with the priority of this other guy and how much interference it causes to this mobile, and then decide its transmit signal is down.
Priority is how to decide.
So priority is what we used in the previous, the 2 centralized schemes. For full buffer is just marginal utility of average rate, and for QoS it's that function of Q length and U length. So these are the 2 functions. And now the 2 things that we convey in this message are, one is the priority you want to convey. The other thing you want to convey is this weight / priority WI times rate that you expect to see if you got to go. And the third thing you want to convey is, let's say this interferer doesn't back off, what is the rate you would see in that case? So that this interferer can now look at the weight times rate that this user would see if it backed off and if it didn't back off, and then compare it to its own rate times the priority for its own mobile. So it needs to do this trade-off. If I back off, I'm going to use some rate times priority for this guy, but I'll lead to an increase in the rate times priority for this guy. So we essentially want to do this comparison in some robust manner, heuristic. So the 2 things you convey is 3 things actually. One is of course the resource. If you don't have enough bytes to send, you content for fraction resource. Obviously you convey the priority WI so that you can make the comparison. And then you convey this nominal SINR, which is the SINR you expect to see if your dominant interferer is backed off. This will actually play a key role. I'll go over this in the point. But then essentially the way to look at it is if my interferers which should back off, this my SINR. And then you basically scale the power of the transferred message in a certain way so that I won't go through the detail. Essentially what you can infer at the interferer are 2 quantities. So the transfer power, if you scale it, can convey some cross-link information. And the 2 quantities which you infer at the interferer are the rate that this link I would see if the interferer backed off completely, and the rate that this link I would expect to see if this interferer transmitted at maximum power. So when for this cross-link gain times maximum power plus the power. So what this interferer will do is now compare 2 things. Let's assume we just receive one coordination message and interferer check. So this I star is just now. So compute 2 quantities. One is the rate that this link J would see if so the gain in the utility or gain in the metric WI times rate that you would get if you backed off completely, and the gain you get when you transfer it at maximum power. So when you back off completely, it's only link I which is going, so it will get this. If you went, it assumes it will get the rate at the nominal interference plus link I would get rate at nominal interference plus interference. Right. So it compares these two quantities and makes a greedy decision saying which of these will matter that it takes the right transfer maximum.
So why should we look at some rate of maybe looking at the other guy's rate also?
So you should look at the other guy's rate because you could not be a dominant interferer to the other guy. So for example, if these two quantities are very close to each other, if your Hij times P max is very small compared to I naught, this tells you are not really causing most of the interference even after I is dominant interference factor. So if these two quantities are very close to each other, then it should go. Because it's not really a significant interference to link I, but it's getting some gain in its own rate times WI, so it should go.
Then it's not greedy, right?
It's greedy in the sense it doesn't do a global optimization. You can get into situations where it's not. But it's using the local information, it does the best in that sense. You don't, so that's why this high star in the sense you just pick one message which you're going to act upon, and that is basically the user to which you cause the maximum loss in priority times rate. The reason you do that is if you start adding up, you may assume 3 guys are getting lots of rate if you back off, but those 3 guys can't go at the same time. They interfere with each other. So it could lead to too much back off. So this just makes it robust. You could look at some other thing where you weight it in some manner for the maximum and so on. But it's just a robustness thing. You just basically essentially say, oh, this is the guy causing maximum damage to, he's going to limit my transmission, then we see if I have higher value.
This seems very myopic, short term. So basically you want to maximize the long term, like average rate. Your utility is function of your average rate.
So convergence apart, we looked at maximizing marginal utility times rate at each time. If you believe that is the right equation, this is what we're trying to do at each time. And then over time, you will essentially.
So W is evolving over time.
W is a function of your average rate.
It's not, I mean, this comparison is not just based on current information. It's taking past information. So it is not myopic analysis.
The dynamics evolve with the purpose. So that's
actually very important because the thing is, you could be in the same, for any pair of links, you could be in exactly the same state from an interference perspective and take different decisions. Because one guy may have backs off a lot, somebody in his neighborhood will be active. And that actually is important too, because you don't want a static resolution of the conflict.
That's why this quantity nominal interference actually plays a significant role. If you increase the nominal interference for all links, you'll get less part off. And you reduce the nominal interference for all the links, you'll get more part. And you want to do this case of topology. I won't go into the specific heuristically used, but essentially the idea is what you want is if you have a link transmitting and someone interferes a lot, you want the strong interferer to back off a lot. But if you have the same amount of interference caused by many interferers using the same amount of interference, you want them to back off somewhat less because now if you have 5 interferers backing off to give you that gain, you go back to the original plot, which was right at the beginning. You lose the degrees of freedom and that very quickly hurts. So the way you tune this nominal interferences on an average, whether you want more back off for this link or less back off, and you use some slow time split topology information to give that. And the third thing you want is if you have one dominant interferer and one non-dominant interferer, you don't want the non-dominant interferer to back off much because 2 things. One is you get a lot of gain by this guy backing off. Second thing is if that guy backs off and this guy doesn't back off, you're stuck.
Again, this nominal interference is these things are this is based on the assumption that the interference is like noise. It's not that doesn't have a pattern and it's not working.
No, it assumes Okay, two things it is. One is that all the interferers will have data to transfer. So you can refine that in the sense at any given time, only look at the topology consisting of interferers and transfer. That's one. And so in that sense, yes, but if you go back to the computation, it's just kind of a bias depending on your topology, whether you want more backoff or less backoff. If you're in a topology where you don't have a dominant interferer and you have a bunch of interferers which are causing a lot of interference, you want less backoff on an average. So this just helps you bias towards more backoff, less backoff. It's not an exact. I don't have any theoretical statement that say, oh, this is optimal. But this is one knob which allows you to.
It's like a soft backing up.
Yeah, control that. If you set this too low, set it close to noise, even guys who are really far off will think, oh, I'm causing a lot of loss in trade compared to when you compare these two quantities to finance. So it will lead to many more people backing off. So it's just a knob which allows you.
So this basically puts the burden of controlling how many people back off somewhat in the hands of the person who's being interfered with. Because he's the one who sets the INOT based on which others react. So, and that is the right thing to do because the guy who's being interfered with is the one who knows how many people are interfering, who's interfering, who's interfering.
So now, quickly go over some simulation. Okay, it's 10 minutes more. Yeah, fine. Okay. So, one mobile person, 9 cells. The reason I restrict to 9 is I want to look at some centralized things as well. But these results scale you, at least through simulation scale you. And you look at the model. Shadowing, we do not model any master. And the deployment model is essentially you place a Femto base station randomly in the square and you place a mobile vector in the square. In the square essentially represents apart from the square. So let's first start with full buffer. It doesn't work for full buffer, there's probably not much what you want to do. With a full buffer, at least you don't take traffic dynamics into account. You just WI times R. So we look at two different utility functions. This is more fair than proportional fair. That is X is the average rate.
By full buffer, you mean always have data transfer.
And what we're trying to do is maximize some of the utilities, average rates, across numbers. And let's look at the rate CDFs again. So this is the reuse 1 CDF, x-axis spectral efficiency, y-axis is the CDF, and the black curve is what you get if you get that iteration in a centralized manner. So at each time if you computed the power, which maximized some of the marginal utility times rate. And this red curve is what you get after the distributions. So you do get some loss, but you at the same time you do pull out the tail quite a bit.
So each time is each frame.
So at centralized each frame you compute the power in a centralized manner. So you compute the power which maximizes marginal utility times rate. Then you go and update the average rates. And your marginal utility changes, again you compute the power which maximizes marginal.
Can you please explain about the probability half for sending the coordinates?
Oh, okay, that's what, yeah. So for full buffer case, there's this, because it's a distributed algorithm, you get this weird consensus issue in the sense I may send a message to another link, and that another link may back off to me to allow me to go, but I may back off to another coordination message I receive. So depending on your topology, you could get stuck in this bad scenario, and this essentially is just some ad hoc randomization over these different patterns. So again, robust.
So if you can do multiple rounds of exchange and coordination, you can work around some of this. will be larger overhead.
Overhead is high.
I mean, the simplest example to convince yourself of the value of this is just take three links A, B, and C, right? And the situation which B says that he's going to go, and A and C back off, but B decides not to go because the guy, let's say C, came in and said he's going. So it'll end up in situations where either A will go or C will go. And in fact, both could always go when B backs off. So it gets you out of those situations.
For a fraction.
So suppose I decided to use a CSMA algorithm for this whatever example you've done. Where do you think the curve will be? I mean, let's take our pick. I mean, whatever CSMA
If
algorithm.
it's full buffer and you have everything, lots of stuff to transmit, and you will see something.
Yeah, I'm just curious because you're essentially sort of emulating some kind of a background using interference measurements, right? So if I just use the completely sort of
So it would be 1 by 9, I would imagine, close to 1.
Yeah. I mean, the setup is such high interference in the situation. You're basically going to be doing 1 by 19. That's essentially what we're doing. And that's going to be very bad. I think what you'll see is...
No, I'm just curious, where will be the CDS?
My guess for this is it would be to the left of the magenta.
Really, you're saying it's going to be worse than...
Because the thing is that the reuse 1, right? Reuse 1 is not... Just because you have high interference, reuse 1 does not become a bad choice. Okay, because the thing is that every time you give up a degree of freedom, you're losing linearity. Right? You're gaining in the log, losing. This, in the case of CSMA or any kind of aggressive back-off algorithm, you gain, like you go maybe, let's say, from minus 5 dB SINR to plus 20 dB SINR, but you shut off 8 links in the process. Okay, so you get your turn only once every month. Once every month. Usually, we have not.
My guess is that you do slightly better here, but lose a lot here.
Yeah, we can plot it.
I'll be curious to see it. Yeah, it'll be sort of interesting to see how sort of a simple algorithm
you've seen these. I mean, I can show you some plots of not this specific case. Yeah, but it basically goes on.
So essentially, this shows that you do get distributed algorithm. It does do something. It's not okay. In the interest of time, I'm actually going to skip over these details and directly go to the performance first.
Maybe you could cover the soft color.
Did you do any case with macro and micro cells? This is 9 micro cells.
This is 9 femtos. We haven't done any macro.
So a general question would be that when you mix this with macro cell, is it really a good thing to do, even if you suppose you could do optimum scheduling and all that? Even so, does this make sense where you have designed a cellular system with certain scheduler and so on? You start injecting these, at least in a backward compatible sense, do you come out ahead of having a separate frequency?
Yeah, that's a tough question to answer. More or less, the requirements on femtocells and operators in place is there should be nothing that prevents them from sharing the same carrier between the macros and the femtos. So a lot of people are working.
I think that would be the first question I'd like to get answered, because operator can always take a 802.11 box, give it to you and call it a femtocell. Customer won't care. But what is the net loss to the operator for putting all these things in? And if that is too large, that is the problem.
I think there's a lot of stuff available on articles written on radar.
Does micro or does this answer most of your questions already?
Yeah, I think there are some techniques very related to this for macro and femto coordination.
So when you do that, my question was if you have different utility functions, because what's going to happen, the traffic in home will be much larger than what you might generate when you're outdoors. So I'm not sure that you want the macro cell be drowned by femto traffic at some point, or reverse, that you have to put so much flow control that people prefer to use other technology.
Right, so that comes down to the choice of the utility function. If it is deployed on carrier, then it's possible that operators would pick utility functions which get higher priority on the macro.
Because I'm still in two minds about this. I think intuitively it's not going to work for that reason, because these have so much more traffic that you'll be destroying the cellular capacity for data users.
So there are things in place where there are requirements in place which say that you have to listen to the macro. The femto cell has to behave like a mobile, listen to the macro, and then set its power so that it does not create like a coverage. So there are all these things that are sort of safety mechanisms that are put in place to protect the macro.
So non-technically, what is the big impetus behind Femto? Why isn't their hotspot good enough? Wi-Fi hotspot?
I don't know the answer.
I mean, it's
good enough for the users, but not for the operators.
Yeah, I think there's just some.
And if the operators have something that's faster, better, fine. But the thing is that having one radio or not doesn't matter anymore.
I think, I don't think it's because of the radios.
I think it's also
probably
because of
just
server inside the building.
I don't think there's a comfort level with Wi-Fi for carrier service.
Because of license, but now you have converted it to coordinated license like spectrum.
Right, that's why I asked about the CSM. Why
I
not?
mean, it's no longer once you have this scenario,
Yeah.
you are doing a distributed algorithm on license spectrum.
No, but it's still, this is still on operator spectrum.
Yeah.
Operator is the one who's, you can't just buy the femto cell randomly.
No,
Operator
so
sanctioned
operator
it.
can put whatever things
Right.
they want in it, but gradually as you put more distributed mechanisms,
Yeah.
operator loses some control.
No, not really, because all of this would be actually, whether you, suppose you do over the air mechanism, right? It will be spec'd up, it will be in black and white, what it should be. And if it's backhaul based, then it will belong in some protocol stack and it will be spec'd out. There'll be interoperability testing that takes place.
So that all part is fine, but you can't guarantee QoS anymore. It depends on the density of deployment, user traffic, and so on.
So
the user experience is not distinguishable from unlicensed plan in some sense.
I'm not sure about how to go that far.
User experience. Operator experience could be that, okay, I can turn off anything I want, and presumably you can clear out your spectrum if you need to. But
why do you say the user? I mean, it's just that the operators. I mean, even in a macro cellular network, can't always guarantee because you don't know.
not guarantee, but there's sort of a range of it.
Right. So this is a bit more of a chaotic environment, I think. But that's the reason why mechanisms of this sort are needed, so that you can bring it up closer to your macro.
So let's answer that, right? Suppose you put a minimum breaking point.
Yeah.
What happens to all the things you guys showed?
So you can make
Yeah,
it.
that's sort of this.
So you can put a minimum rate requirement very easily in this framework, making the utility function blow up at the minimum rate.
That's one way, or you can even look at token-based mechanisms.
So what will have to be done is, so right now the macro network, there is a QoS framework. So you have to take that QoS framework and map it to the utility functions. And then it will, when it's feasible, it will give you that minimum rate. When it's not feasible, it should degrade these. Which is pretty much the same thing as the macro.
Yeah.
In fact, it's possible that with the duty cycle of these femto cells, it's possible that you hit your QoS with a higher probability here than you would in a macro network. And the high loading, you're not likely to get the best QoS. But the level of reuse of the spectrum that you get with this kind of a deployment is just so high that ultimately.
So that part is the moment you put it into homes, the traffic is going to go up by 2 orders of magnitude if it's useful to me as a gateway into broadband.
True.
So that part I'm worried about. And trying to put all that to the same license spectrum, which is finite to begin with.
Yeah. So I mean, there could be some middle ground where for the heavy duty video streaming type of applications, it may switch to Wi-Fi, and then for more, QoS dependent activity, switches to the Femto operation. I don't really know how that's going to play out in the marketplace.
This is an interesting technical discussion, but I'm not sure about the product.
From
any deployments?
Yeah, I mean, Sprint has had a deployment for a while now. Verizon has had for at least 7 or 8 months.
It's a
Where?
trial region.
They're selling it to.
So they can go buy a Femto cell?
You can go buy a Femto.
And so how does it work? I mean, so I sign up for some data plan or something? Or how does the
I
pricing
think,
work?
right, I don't know how the pricing works. I don't know. So, but you can look up this network extender with Verizon. Right now it costs like $250. And it does only 1x. It doesn't even do keywords. Similarly, Sprint has some.
T-Mobile has this Wi-Fi kind of solution. You can buy this box at home.
So if somebody has Wi-Fi at home, why would you do that?
I think that's so much conflicting with this. Because the two will work together. One of the reasons behind this is also to reduce the cost of the network operating infrastructure.
Exactly.
Because the base stations are expensive.
Exactly. I mean, today you have the limiting factor in the.
No, the idea is that everybody will go for this.
It's the back
They won't get any wireless.
because those are actually even lower than multi-gigabit hosts. So this opens up all that possibilities.
So it's not conflicting with that.
Because,
Yeah, because we're not upgrading the platform.
So, do you guys have any idea, I mean, this is sort of a question for your business unit, right? If somebody has a Wi-Fi already, and Wi-Fi has a certain penetration at home, right? What would make them sort of want to go buy this instead of that?
I mean, that's really the place that, so that's not an easy